So when an electron drops from a higher energy level, a photon is released, and one photon, I should say. So the energy of an electron is equal to this equation. We've been seeing this, and remember it's negative. The change in energy for the electron, we're going to take, this is the kind of the final minus the initial, and this is for the electron, so that makes sense. That's the change in energy for the electron. But the energy of the photon is not, it's this same number, but the opposite sign. The electron is giving it off, the photon just has the energy. So I took this and I put a negative in front of it, and then I rearranged it. And so this is the equation that you use in lab. I wanted to show why the energy here is kind of, it seems like initial minus final, which seems wrong, but these actually are for the electron and this is for the photon, so there is a difference. In the lab manual, it just shows this. It shows this, which I think that should be fixed, but it's not up to me. This really means energy of photon. Okay, and then they have you calculate it this way. Okay. So if an electron is absorbing energy, the change in energy is positive for the electron. If it is emitting energy, the change in energy is negative for the electron. Okay, this chart will be helpful in lab to kind of figure out what's going on. So the first thing I want to point out is that these energy levels are not evenly spaced. When I drew it earlier on a slide, it wasn't really to scale. I think this is a little bit better. But the idea here is there's a lot of energy difference between the first and the second, a lot. And then the second and the third has a little less. But then as you go up, they get closer and closer together. Okay, and how that affects things is that these are the possible transitions for electrons. Like if an electron goes from the second to the first, or if it goes from the third energy level to the first. Okay, and because of the spacing of these, what happens is that all of the transitions where they end here at the first principal energy level, n equals 1, those all involve higher energy photons than any of the transitions that end at 2. And those are all higher energy than all of the transitions that end at 3. Okay, so we have this pattern where the amount of energy in a photon really just, like when you're comparing transition, the most important factor is where it ends up, which energy level it ends up on. So notice that all transitions that end at n equals 1, so this series here, these are all falling in the UV range. The photon that they release are all in the UV range. These, the Balmer series we call, these are the 4 visible wavelengths of light that we'll observe in the lab. So the ones that fall in the visible range all end at n equals 2. Okay, and then these up here, the ones that end at n equals 3, they fall in the IR range. Okay, so for lab, yours will fall in IR, visible, VIS, or UV. And you'll see that when you look at the wavelengths. I do have another video that covers this, but this these two slides, actually, the one before and this one, will really help you do all the calculations that you're going to do in lab for the hydrogen line spectrum. And you're basically going to use these equations in order to do all of those calculations. On this one, this is where the lab manual says delta E. When it says upper and lower, it's talking about the energy level. And anyway, you can look at the next video to see all these calculations.